Hey guys, welcome back to Introduction to Computer Networks. And this is week 6, episode 11. So we have only one assignment this weekend. That is quiz 14. You guys should be able to complete today or later today. And a little bit of a heads up for next week. PA4, which is the second hardest PA for the whole semester. It will be due next Saturday. And those are keen preparing for the exam one. Yeah, the exam accounts are ready. And if you go to channel exam 1 here, yeah, so Yixin, sorry that the availability of the exam account this semester is a little bit implicit. Because Poly decided to change the way announcing the exam accounts and the passwords. So there's no longer a default password that you need to change immediately. This semester, Poly wrote some scripts so that I can automate the process, including sending you guys emails informing you guys the username and the password. So the password for each of users' account is different this time. Okay. So you can keep it or change it to something that it's easier for you to memorize. Either way is fine. All right, so the exam accounts are ready. So the username and passwords are sent to your NTU email account. Okay, so this is the default one. So your student ID at ntu.edu.tw. Okay, some of you do have a Gmail-based NTU account. Okay, that will be still your student ID at g.ntu.edu.tw. Okay, I do see that some of these emails sort of bounced. So I guess some of you guys don't have the g.ntu.edu.tw email set up. Okay, but either way should be fine. So if you don't see an email from Poly, okay, informing you of your username and password, definitely let Poly know. All right. And these accounts are already available. Feel free to log in and start fooling around, or hey, upload things that you thought that it might be useful ahead of time. All right, so what's very important is that, hey, make sure you read through the exam rules and requirements that's posted earlier on the exam 1 channel, as well as on the course website. So they are the same. Okay, what you see here earlier, okay, is already said on the course website. You just need to read one versus another. Okay, I think we went through bullets 1 to 4 last week. Okay, what's more clear is the scope. Okay, we would actually the exam scope is up to 2.5, chapter 2.5. Okay, and bullet 5, 6, 7, 8, 9. Why don't we come back to go through these, as well as what Poly has added as a post at the end of exam 1 channel is how it's gonna be like during the exam. Okay, what the process is gonna be like, so that you are more mentally prepared what's gonna happen. All right, I understand that this is probably one of your first, for many of you, the first time you're taking an online exam. Okay. So, hey, it's a little bit unusual, all right? But it's not exactly hard. But after we finish chapter 2.5, we'll come back to these bullets and go through them one by one. And yeah, many of you pop up. That's great. Good to see you guys, because today is kind of important, all right? In case you have any questions related to the exams. And with that said, let's go ahead and jump into the topics today. We need to finish chapter 2.4 and finish chapter 2.5. By the way, we have 5 topics today, but we'll probably skip Skype, the last topic, so that we have time to actually walk through these the exam process. Good. All right, so we're almost done with DNS. There are just 4 short videos left, each of them about 2 minutes. Okay, the first one is to talk about these entries. Okay, host name to IP mapping entries. So there are many entries maintained on the DNS servers. And we know about the host name to IP address mapping. This is just one type of the entries. There are actually 4 types of these. Okay, so this video, 2 minutes 20 seconds to introduce the other 3 types of entries.
Let's take a closer look at the entries that DNS servers are storing there. They're called the records. Okay, well, to be more precise, the resource records. Okay, and each look like this: a tuple of 4 elements. This is usually the host name, and this is the IP address, and this is TTL, the time these entries should stay on the server. What we haven't talked about is this type. There are actually 4 of them, not many. Let's look at them each a little bit closer. So first is type A. It's the most classical one, which says host name and the name, and IP address and the value. Essentially, this is the query, and this is the answer. Querying for this host, answer is this IP address. Second type, let's go here, the C name type. What C stands for is the canonical name. So what this does is corresponding to the second service we mentioned way earlier when we started talking about DNS. So it's doing what? Alias, the name alias service. So what it does is here, the entry there, name is the alias, the Q short one, and the value is the actual name, the canonical name, the real name. So here we have .ibm.com, cute and short, easy to memorize, but the actual name for that machine should be this, server is backup to the ibm.com. Right? So value is the canonical name. Third, let's look at this type, the MX type. So this is mail service type, and this corresponds to the third service that DNS provides. Name is a domain. Value is the mail server for that domain. So name here could be gmail.com, and the value will be what? smtp.gmail.com. Straightforward. Last type we have not yet talked about. It's actually not quite the fourth service that we mentioned about DNS providing. It's actually called the authoritative name service entry. Right? So the name there is a domain, okay? But it's not the top level domain. It's usually the second level domain. The value is the host name of the authoritative name server for that second level domain. So this is for the TLD servers to store all the authoritative name servers for all these subdomains. Right? So NS type entries are mostly in the TLD servers.
All right, so essentially all the 4 videos today about DNS are more on the data side. Okay, so those are the 4 types of DNS entries. Second is, if you recall last week, right? So to get DNS servers to help you, you need to send a query first, and the server will send back a response. Okay, so there seems to be 2 messages, okay, that's flying around between the client and the servers. But you know what? In DNS, there's only just one message format. Okay. In this video, also 2 minutes 20 seconds, you will see how the format is like, so such that it serves both purposes.
Next, the DNS protocols messages. So the servers exchange just the query and the reply messages to each other. They are in the same format, which is exactly what I'm showing here. There are 2 parts though. From here and up, this is the message header. From here and down, the data part, where the actual mapping, actual entries are being carried. Now let's focus on the header a bit more. The first field is called the ID. It's 16 bits long. It is used to identify a pair of query and reply. Right? Next in the flags, then you identify whether this is a query or this is a reply. So this is how server know that, okay, this reply is for a query that carries the same ID. In the flags, you might also see a certain client is saying that, can I do recursive query? In the flags, you might also see certain DNS servers saying, no, let's disable a recursive query. And coming from the authoritative DNS server, you might see this flag being turned on. The reply is authoritative. Right? There are 4 other fields in the header, these. So these are specifying the number of questions, number of answers, number of authoritative replies, number of additional informations. Now these are to serve the purpose down here in the data part, because the number of questions a DNS message can carry is variable. Now in order for the receiver to know how many lines, how many records it reads, it looks up here to find out and reads up to this point and then to the next part. So that you will not be confusing a regular reply with an authoritative reply. Right? And next, let's focus a little bit more in the data part. Okay, so in the question fields, you will only see this, the name and type in a query. That's all. There's no value, there's no TTL. In the answer entries, however, then you see the full RR, the full resource records. Authority here carries records for the authoritative DNS servers. If you have also the full RRs, it's just that those RRs are the authoritative server RRs. Last is just additional information. I see rarely this part of the data being used.
All right. And next is, hey, these messages will get responses, queries will get responses. And therefore, at the local DNS server, there'll be these entries available. And the local DNS server, if you heard Polly saying already, the local DNS server are essentially a big cache, okay, of all these entries that the clients have requested before. Now, how we maintain the cache on the local DNS server, however, are very different from, you recall that we talked about another caching that we did for the web service. Okay, so the web caches. When we maintain the web cache, the proxy server does this. In order to make sure that the cache copy is up to date, the proxy server will send a if modified since to the origin server to confirm, isn't it? That is because the web pages nowadays can change quite dynamically. Okay, but the DNS entries, okay, they don't change pretty much. If they do change, that's usually once a month, once a year. Okay, depending on the type of the service, depending on how resourceful the companies are maintaining the service. Okay, so they don't change often. Therefore, the DNS cache, okay, is maintained another way. Okay, and they use a timer, okay, to track, okay, how long these entries would expire. When it's time to expire, the entry removed. Okay, so a very different way of maintaining the cache. This is the DNS cache.
DNS servers also cache data. And this is not the first time we hear this term caching. The first time is when we were talking about web caches, isn't it? So web cache there stores web objects so we could reduce delay. We could save some network bandwidth. You see here, DNS, for the same purpose, also caches IP, name, mappings. Okay? The goal is also to reduce delay to save network bandwidth. So you see, caching is actually a very general technique for data transferring services to try to avoid repeated download. So let's go on to DNS caching. So each of these mapping will be stored at the name servers once they acquire them the first time. So these entries will be there on the server's disk for some time. So the interval is called the TTL. What it stands is time to live. So during this time, the entries stay. Once the time expires, the entry is timed out, removed, okay, from the entire disk. So an example, a local name server might store the mapping for a top-level domain server so that the local name server doesn't need to go to the root name servers a lot. Okay, again, trying to conserve the root server's capacity. Right? And the cache entries may go outdated. This is happening when the entry is not yet timed out, but the host there is already changing the IP host mapping at the authoritative DNS server. In that case, the clients worldwide will continue to get the old mapping, the out-of-date mapping, until 2 days later. This is usually the TTL of DNS mappings are set to by default. So 2 days later, the clients get the new mapping. So that's why we don't change the hostname IP mappings all that often, because during these 2 days, your customers will have trouble reaching you. So DNS caching, this is another protocol. It's defined in this RFC 2136. And by the way, the body, the community defined all these internet protocols. Okay, writing all these RFCs is called the IETF, the Internet Engineer task force.
All right, so that was caching. Okay, the last video is actually not to teach you how DNS works. It's more to give you a sense when you are starting up a company, how do you set up the authoritative DNS server for your company? Because, hey, for your company, you would have a website and the server's IP that you need to maintain a mapping of the website, the domain, and the IP address. Okay, and therefore you need to set up a DNS, authoritative DNS server. But in addition to doing that, you also need to report the top level domain DNS server, a couple entries, so that the rest of the world will know by querying your domain recursively or iteratively, eventually to find where the authoritative DNS server is, and therefore find the IP addresses of your company's website, isn't it? Yeah, so that is what this video is about. It's 2 minutes. And guys, there's a pop-up quiz on the YouTube chat as well. We did not talk about UDP or TCP that the DNS messages are sent through. Did we? No, we didn't. Okay, so I ask you to guess. I'm not going to talk about it. Okay, in fact, the textbook was not explicit about how the DNS messages are sent yet. Okay, we'll talk about that, however, in chapter 4. So while you are going through this video, it's just for your information. Guess which one, UDP or TCP, the DNS messages are sent through. Okay.
Now let's try to put our knowledge into use. So here the scenario is you need to set up your network for a startup, network utopia. All right, so 2 things you need to do. First, register your domain name with the DNS registrar. Now, being a .com, you talk to this company, Network Solution, who maintains the .com TLD server. Right? Second, you provide also the name and IP address mapping of the authoritative DNS server you'll be setting up. Okay, so there could be a couple of them just in case the first one failed, there's a backup. At this point, the registrar there, the Network Solution there, will try to insert 2 records. Okay. One is, of course, the name and IP address mapping. Second is the domain name and the host name of the authoritative server. So you see here, name to IP address is the type A, the classical one. This one here is the NS type, the authoritative type, where the TLD stores domain name and the authoritative DNS server mapping. Good. Now, back home, you need to set up a couple of these authoritative servers for sure. But inside these authoritative servers, what do you store? Well, if you want a web service, you need type A entry that keeps the name of the web server and the IP address of the web server. If you wish to have email service, then you need to set up an MX entry maintaining the mapping from the mail domain to the mail server's host name. And maybe the IP address of the mail server entry, that's another A record in the authoritative server. All right, so that's how you get your customer to see the IP address and therefore being able to visit your website.
All right, so that's all about DNS. Okay, and I see, yeah, some of you guess TCP, some of you guess UDP. Okay, and I think some of you guys argue. Okay, for example, Boyu says TCP because reliability is important. You know what? I agree. And Ivan says TCP. Excuse me. You want to make sure the data integrity. This is very important these days. Do you care about privacy? Some of you probably do, right? We won't be doing that in this course, but it's actually quite easy for people on your subnet to sniff the traffic you send. And from seeing the DNS responses going back to your machine, they learn also quite a bit about you. Does that give you some creep as well? Yo Cheng says, I guess UDP, you can tolerate the loss. Interesting. Yeah, I mean, recall, right? When you guys are asked if you're designing different kinds of games, right? In particular, the shooting game. Yeah, shooting actions are important for shooting game, obviously, right? And we definitely want it to be reliable, but between timing and reliability, or the textbook said data integrity, timing can be more important. So maybe we do want the DNS reply to come back as fast as possible. If we use TCP, then we need some time to set up a connection. And then you send the request. And for UDP, for DNS query, it's short message go and short message back, and that's it, right? Wow, setting up a connection just for such a short exchange. So I think Yo Cheng, you have a point as well. Yu Zheng says, if the packet get lost, just send it again. Yeah, so Yu Zheng, this is exactly the point Polly was trying to bring up. So you know what? Once again, what you're seeing is that, hey, there's strengths using TCP, there's also strengths using UDP. And a lot of time, eventually, whether it's UDP or TCP being used by a protocol, it's really up to the designer. The designers will need to analyze the trade-off and decide. And guys, hey, I'm asking you to guess the eventual answer currently on the internet. UDP is the protocol to send the DNS messages. But guys, UDP is the protocol to send DNS messages from your operating system, okay, without any changes. But more and more people today encrypt the UDP, the DNS requests. It's called the DOH or DOT. Guys, look it up. This is sending DNS over HTTP, secure HTTP, DNS over HTTPS. And DOT is DNS over TLS. And what is TLS? It's the encrypted version of TCP. So nowadays, people value security and privacy more. So in practice, many people configure such that all these DNS requests go through DOH or DOT. And that is in line with the students saying, no, I think TCP. And in fact, not quite TCP, not quite UDP, TLS. Because HTTPS is running on top of TLS as well. All right, get it. So, hey, again, internet protocols, they are also dynamic targets. They are being changed, revised, amplified, okay? So, moving target. Now, let's move on to the last topic, okay? No, actually, this is not the last topic in chapter 2. It's the last topic before exam 1, however. Okay, so it's called peer-to-peer model. So all the applications we've talked about so far are client-server model. P2P is the other one, right? In P2P, there are no longer these always-on servers. We have just peers. And you know what? Peers are just like you and me. And we are online sometimes, we are offline sometimes. So these peers come and go. And how do you maintain a service with such, dynamic peers, okay, running around? It's actually a challenge, all right? So in this introductory video, 2.5 minutes, you will see Polly giving you an overview of P2P. And in the second part of the video, Polly will give you an example application of P2P. The most popular one is file distribution, and particularly for large file distribution. For example, a video file, okay, or a big software. So to distribute such a large file, okay, coming from a server and with many users, okay, it can be very time consuming, okay, until all the users download the file. Okay, so in the second half of the video, you will see Polly giving you also a setup, giving you a pictorial view of what the problem is. And so later on, we'll compare how client-server mode to distribute a large file can be slower than distributing large files in a peer-to-peer mode. All right, so this video, once again, 2.5 minutes.
P2P applications. To be honest, this is one of my favorite sections in Chapter 2. All right, so P2P architecture. As opposed to the very simplistic client-server architecture where we have always-on service, in P2P, there's no more always-on servers. Instead, we just have these arbitrary peers directly connecting to each other, communicating to each other. As you see, hey, these peers are very likely mobile end systems. So the connectivity there is intermittent, meaning loosely connected, on and off, on and off. And the IP addresses to establish physical connectivity can also change over time. So it's actually hard to maintain a fully connected session as a user moving around, for example, on NTU campus. So we'll talk about two applications. One is for file distribution. The other is for voice service, voice over internet service. So the application for file distribution is BitTorrent, and the other one is called the Skype, an internet telephone service. We're not going to talk about applications in video streaming, but there are actually quite a number of these video streaming systems in the early years that works in this peer-to-peer way. So for example, this one, Kankan from China, that's Mandarin Chinese, meaning take a look. It was a very well-established service. Okay, before we talk about all these P2P application examples, let's talk a little bit more about the benefit of shifting from the client-server paradigm to the P2P paradigm. Right, there must be a reason why people choosing to do P2P instead of client-server. And we're going to use an example, very simple, to transmit or to distribute a file from one server to end users. Right? Each of these users will be limited in terms of the uplink as well as downlink capacity. So look over here. This is peer I. Okay, so its uplink capacity is called UI, and downlink capacity DI. Okay, so the same fashion you see therefore for user 1, uplink bandwidth being U1, downlink bandwidth being D1, and same for user 2 and user N. The server is over here. The uplink capacity is US. Well, therefore, the downlink capacity is DS, although that we're probably not needing it in the calculation. All right, so file, one big file, size being big F. So this is the setting.
All right, now let's check out how much time it takes to download this big file F to N peers in the client server mode.
Now let's calculate the time it takes to distribute the file to all end users. First, assuming client server model, meaning server here will need to upload a copy and distribute it to each of the clients. If the uplink capacity is US, therefore the time to send one copy will be F over US, and to send N copies altogether, NF over US. And this is the term that we have here, because the overall file distribution time will be limited by the uplink capacity and the minimum client capacity. So this is the case where the server is the bottleneck, and this is the case where a client with the minimum downlink bandwidth is the bottleneck. Now, the client carrying the minimum download rate, let's assume the value is d mean. Therefore, the download time is F over d mean. The smaller the d mean is, the longer the download time is. And therefore, you see, again, in case the server is the bottleneck, the overall distribution time will be bounded by this guy. If the client is the bottleneck, the overall distribution time will be bounded by the F over d mean. Now, that's considered an N that's increasing over time. Right? Talk about the scalability of the system. The file distribution time, how does it scale with N increasing? Well, this term suggests the overall distribution time will increase linearly in N. While the minimum bandwidth for downlink might not change all that much. Okay, so Potentially the overall delay, if we change n, is growing like this.
Yeah, so in client-server mode, big N is the determining factor. Now, how about the peer-to-peer mode?
Now, the same, calculating the time for file distribution, but this time in the P2P model. Meaning, hey, this is one of the peers, and each one of these users is also one of the peers. So they could be downloading a copy from the server, but they could also be uploading a copy for another peer. Now, the server transmission time, this part now, the optimum is just to send one copy uplink. So F over US. Client there, in case it's the bottleneck, it's going to be bounded by F over D mean, which we explained. And clients overall as aggregated system, okay, must download NF bits, okay, and the maximum upload rate is the sum of all the uplinks for all the users plus the uplink capacity of the server. All right. So in a way, the file distribution time here for a P2P system, it's bounded by either bottleneck at the server, bottleneck at the client, or bottleneck as the system as the whole. If we want to download NF bits over this much bandwidth entirely, right? So we have the server being the bottleneck case, one of the clients being the bottleneck case, and the system overall being the bottleneck case. So NF bits that needs to be passed out, okay, over the entire capacity, entire uplink capacity of the system. Right? So the distribution time bounded by one of these two terms. All right, now consider again, if n is increasing over time, right? The scalability of the P2P modeled file distribution system. Which of the term you think is going to grow with the n? Yep, this one over here. Right? It also grows linearly with the n. But if you look closer, when the number of users also increase, this term also increases. Yeah. So does this. And each peer brings service capacity. If you recall, this is also what was talked about called the self-scalability, a nice property of P2P architecture. Okay? As a peer join, right, the peer demands service, but the peer also contributes its own uplink capacity, okay, to help others to download. Okay, so this grows linearly with n, but this also increases, but not quite sure if it's growing linearly. But overall, it's going to be better than what? The linear growth. So the growth is probably more like this.
All right, so the last video of P2P overview is just to show you quantitatively that the distribution time in client-server mode is linear, and in peer-to-peer mode is sublinear. Self-scalability again.
Let me use a very simple scenario to contrast quantitatively the differences between client-server mode and P2P mode in terms of the distribution time, right? So scenario goes as this. The client's upload rate is small u. And if we want to upload the file over this client link, F over u, and let's say that that's 1 hour. And the server uplink rate is 10u, 10 times higher than the client's uplink rate. And let's assume the downlink capacity of all the clients are just so large, much higher than the server uplink rate. Right? So bottleneck is actually here, the user uplink. Right? Now, think. Let's assume that there are 10 users. Okay? In client-server mode, what is the distribution time? So let's see. 10 users, 10 copy of the file, and the uplink capacity of the server is 10u. Therefore, what? F over u. And this is 1 hour. So in this case, yeah, the distribution time is 1 hour. Clear? Now, in P2P mode, let's see. We have what? 10 files, 10 copies of the files that needs to be downloaded overall. All right. And what is the total uplink capacity of the system? So user has 10u. Each client has what? 1u. So 10 of them, also 10u. Altogether, 20u. And how much is this? Half of F over u. And this is what? Half an hour. And is that right? It is right? In P2P's case, 10 users, only half an hour. Okay? So you see, the growing trend, linear in client-server mode, but sublinear in P2P mode. And this illustrates this characteristic of P2P system very well, self-scalability. Right? And this is the big advantage of running an internet service in the P2P architecture over the client-server architecture.
All right, so the magic is this. I think Yixin is asking exactly this. In the client-server mode, each of the clients would just be downloading and downloading, okay, getting and getting. But in the peer-to-peer mode, everyone is peer. There's no like always on server, and everyone is a client as well as a server. So each peer would be downloading the file from somewhere, not just from the original server. Once one of the peers have a chunk of a file, hey, that particular peer can also serve as a server, allowing other peers to download that chunk. That is saying that the overall uplink capacity is no longer just the uplink capacity from the server. Every peer's uplink capacity can be used, okay, to distribute the file as well. Okay, therefore, the aggregated uplink capacity to allow file distribution is now higher. Okay, not just from the original server's uplink capacity. I hope that I answered your question, Yixin. And in case this is not clear for you, the rest of the class, that's the main difference between a peer-to-peer system to the client-server system. Everyone is equal. We take from others, but we need to also help each other. Otherwise, hey, you will see a P2P system with selfish peers ended up going nowhere. Okay, so we'll see that from an example. It's called BitTorrent. Okay, this is a very popular P2P system. The first video introduces BitTorrent. In BitTorrent, a large file is divided into chunks. Okay, and everyone is fetching a chunk at a time or allowing other to fetch a chunk at a time. So in order to join a group of peers distributing a file, one needs to identify the tracker for that particular file. So in a tracker, very often there are different files, and the tracker maintains, hey, where is the peer group, okay, that is circulating a particular file, okay, and that peer group is also called a torrent. Okay, so 3 notions in this introductory video. Chunks composing a file. You have a tracker that maintains the mapping of individual files to its torrent circulating the file.
First example is BitTorrent. The way the file is distributed in BitTorrent is, instead of sending one big file at a time, it's divided into smaller chunks, 256 kilobytes per chunk. And the peers in a torrent actually sends and receives these file chunks. So here's to illustrate the P2P network. Okay? And each of these is a peer. Okay? And the group of peers form a torrent. Okay? And they exchange chunks of a file. Okay? So BitTorrent. Okay? Now, there's one more entity. It's called tracker. So this machine here is actually to bootstrap the process of having a new user joining or a new peer joining the torrent. So when Alice arrives, for example, what the system does is to first, okay, contact the tracker, and then tracker in return, okay, giving Alice a list of the peers. Okay, and this is the initial set of peers that Alice will connect to. Okay. Now, once Alice is connected to the torrent, then Alice can try to explore other peers and then establish connections to these other peers. So, tracker here is to bootstrap the initial joining process. Furthermore, about the operation of BitTorrent. A peer joining the torrent, yeah, you've heard it earlier, right? Contacting the tracker to get the initial set of peers. And those peers that are connected to Alice will be Alice's neighbor. Okay. And Alice at the beginning has no chunks, but over time, Alice will accumulate these chunks and eventually growing into a complete file. Now, the general operation is this. Each peer will be downloading the chunks while they are also uploading the chunks to other peers. And the peer and peers exchanging chunks, the pair could change from time to time. So they may change the peers with whom they exchange chunks. And the peers might just go away and come back in the middle of the exchange. That could be a bit disturbing. There's a special term for it called a churn. Okay? Hopefully there's less amount of these churns, but sometimes it's not really controllable. And in the end, once the peer has the entire file, for a selfish peer, he or she might just leave the P2P network entirely. For those who are more considerate, they might remain on the torrent.
All right, so you see that, hey, there could be selfish peers. But no, wait until the second video. This one is a bit long, about 5 minutes, because in BitTorrent, so a peer, if you join, then there'll be many chunks that you would like to download. So do you download or request sequentially from chunk 1 to the end? Well, careful, because there could be selfish peers. There could be certain chunks that many of us don't have it. Okay, very few. And you do what? You do want to fetch that chunk first before the peers, the few peers holding the chunk, run away. So there's a certain strategy to decide which chunk a peer fetches first. There's also a certain strategy. A peer can be asked for chunks. So upon all these requests, which peer's request would you like to serve first? Okay, so there are 2 parts, and each of them would definitely invoke you to think about, how come such design? Okay, so let's check this out.
The part that Polly finds the most interesting about BitTorrent is this. The strategy to request chunks and the strategy to send chunks. Let's talk more about the requesting strategy first. The setting is this. Given a file that many of the peers are looking for, so they'll be downloading chunks for the file. At any given point in time, because they're doing the downloading independently and they might be connecting to different neighbors, they might not know each other, so at any given point in time, different peers might hold a different subset of the chunks belonging to the file. And the way it progresses is each peer then will periodically query the neighboring peers. So asking neighbor 1, neighbor 2, and neighbor 3 for the set of chunks neighbor 1 has for that file, neighbor 2 has for the file, and the set of chunks neighbor 3 has for the file. Okay? So it's kind of an inventory check. Now once the peer receives all these inventory check reports, the peer begins to count which chunk is the rarest in the P2P network. And the peer begins to download from the rarest that he does not quite yet download yet. So that is the requesting strategy. Now if you think a little bit more about it, why rarest first? If I tell you, look back the previous slide, the issues we might run into are these, right? A peer might come and go, right? So as they move from one subnet to another subnet, it might get disconnected, the IP addresses might get changed. If it's in the middle of the download, those chunks will disappear from the P2P network. Also, right, when some peer finish downloading all the chunks to a file, and if the peer is selfish, they might just leave the network entirely. So in a P2P network, real users will all have this anxiety of not being able to find a specific chunk for a file. And that is also when BitTorrent downloading can go really, really long. It's not because there's not enough capacity, but it's more. Certain chunks are no longer there on the network. Okay, so it's actually quite important this rarest strategy is implemented on a P2P network like this. Right? And another aspect that's interesting is the sending strategy. And I love the name, tit for tat. It sounded kind of fun. Right? The way it works is also very simple. Alice here as an example peer, she will send chunks to others that are sending back to her at the highest rates. Okay, so hey, if you're generous to me, then I will be generous to you. Okay, eye for eye, tit for tat. But this simple strategy might create this problem. Other peers are not sending at the highest rate, will be choked then. These guys might not get a chance of downloading certain chunks from Alice at all. Right? This is actually not quite that good. So Alice will reevaluate, okay, the top 4 every 10 seconds. So those peers who discover that they're choked, they're not downloading any chunks, they might decide to contribute more uplink capacity. Therefore, as a result, they might get some chunks from Alice back the next round, the next 10 seconds. Okay, so this is the general strategy. Okay, share your uplink bandwidth, then I share mine. But this might not be a good thing either, because some of these peers might be very non-resourceful, meaning they have very, very low uplink capacity. As a result, they might always come up short here in the competition for the highest rate neighbors. So every 30 seconds, Alice will be very generous, okay? And not look at the sending rate coming from the neighbors, but just randomly pick one of them and start sending chunks to them. So optimistically unchoke, okay, a particular peer. Now the newly chosen peer will join the top 4 and receive chunks from Alice. Right? But this is done at the lower frequency, only every 30 seconds. Right? So mostly favoring those who are contributing more bandwidth for uplink purpose, but every now and then, not bias on the uplink capacity of the peers and openly share. Okay? Interesting, isn't it? And let me animate tit for tat here. So Alice here optimistically unchokes Bob. So Bob could be a newcomer into the network. Okay, Alice might randomly discover, okay, there's this guy Bob there. Alice begins to send chunks to Bob. And Bob there says, wow, thank you for all the bandwidth, all the chunks. Okay, and begin to send, also at a high rate, back to Alice. So mutual appreciation at the end. But Alice needs to be optimistic at the beginning, right? Trying to have faith, trust that whoever receiving the data would appreciate the effort. So higher upload rate finds better trading partners, okay? And so you get files faster this way.
All right, so tit for tat, if you think about it, that's a little bit like how we make friends, okay? So we go to places and run into people, and you talk to them, interact with them, and you keep some of them as your friends. And then you go on every now and then to meet new people, and you keep some of them, and so on and so forth. All right, good. And next is to go to quiz 14. You know what? And quiz 14 this time is going to be a take-home quiz. So occasionally, we'll have these take-home quizzes for the sake of time. So what you will do is go to the scoreboard. Quiz 14 is already there. And let me explain what the... Oops. I see. Okay, 1 second, please. You see that, let me go through it. Okay, so this is quiz 14. People come and go, but so are these BitTorrent trackers, okay? Because this is the one key information you need to get first before you can join a torrent, before you can download a file you're looking for. And these trackers, okay, many of them are gone, so supernova.org, torrent spy, low-key torrent, these are all gone. But one struggles. Okay, it's still around in the poly check this morning. Pirate Bay is still there, but the domain name is no longer the piratebay.se. So this used to be a very popular domain, but the Swedish core has ruled that this domain, okay, should be shut down, okay, because there are many content being distributed with the help of the piratebay.se that are illegally distributed, okay. So, but this reporter is interesting. So Andrew Griffin, by saying this in the title, but site likely to pop back up again elsewhere, okay. And that explains why Pirate Bay is still around. But guys, be very careful going to these websites. There could be malwares that you can download by accident. Okay. All right. So what I'm trying to ask is this. Okay. Thinking from the point of view of trying to keep the Pirate Bay around. okay, to share information that is probably hard to distribute otherwise, legal or illegal, okay. It's easy to kill a tracker, okay. So that's the bad thing, okay, thinking from a pirate-based point of view. Q1 why are these high-profile trackers shut down? So this is definitely not a technical question. So I'm just asking so that you're exercised, thinking about why the government would like to shut down a certain website. Okay, what's wrong? Q2, how to make the trackers hard to shut down entirely. Okay, and guys, if you go to the Discord space, yeah, okay, I see some of you guys already posted your answers, okay, which is great. We'll come back to go through what you guys have to say next week, all right? And we'll use the time, on the other hand, to go through the things that many of you are concerned about, which is exam 1. So let's go to point 6 up here, 5. Okay, so first of all, the exam is super long by design, okay, because the exam is open internet. Okay, open internet, other than just that you guys cannot interact with each other, but all the other access of the internet is allowed. Okay, and therefore the exam is super long. And so if you couldn't finish the exam entirely in time, it's completely normal, okay? You don't need to be nervous. You are only compared relatively to other students, okay? Point 6 is asking this, okay, because we're using a Google form. And Google form, if you fill contents on the Google form without submitting, and if you lost the Google form website, whatever you've inputted earlier will be gone. So in order to make sure, okay, whatever your input is registered to Google, okay, you want to do this. We advise you, after you fill the basic info and submit the basic info like your name, student ID, email address to contact, you submit the empty form next immediately, okay? By doing so, you will get an email coming back to you to the email address you leave on the form. And that email will contain the link to come back to the form. So that if you lose the web page or accidentally close your browser, it will still know where to come back. All right. So if you lose the form, it will be just for a short term. So in the middle of the exam, after you already input a good amount of data, make sure you submit again. Okay, that will register whatever you have into Google's database. Okay, so it is advised that you do this frequently. Okay, although it would take time for the form to upload, but that amount of time that you lose is probably a good trade-off to make sure that the data, okay, in the Google database is up to date, okay, or as complete as possible. And by the way, after the exam completes, we'll be checking the timestamp on the Google form. Okay, so Google will track exactly the time you've submitted the form. And there might be a couple seconds delay because it takes time to upload the form. Okay, and we'll, there's a 5-second grace periods. But after that, know that at the beginning of the semester, we've already communicated that the points will be deducted if you submit the form late, okay? And how many points for how late? Recall, okay, the rule again, okay? So I'll let you read this out in more detail afterwards. So after you click the submit, you will need to pass the Google CAPTCHA, okay? Some of you might be challenged, okay, but some of you might not be challenged with the CAPTCHA. Either way, the safe approach is submit first, okay. If you be prompt for CAPTCHA, you will know early on, okay, and you will pass the CAPTCHA. And later on, I think Google will probably go easier without challenging you with the CAPTCHA every time you submit. Okay, and there'll be questions testing Golan syntaxes. Okay, so those syntaxes that are required for PA1 to PA3. All right. So you will receive an account, and it's an individual account for you to work on. Okay, for the exam. Okay. So I said here 2 SSH sessions maximum during the exam, but I guess many of you guys are using tools, okay, that uses SSH to upload code, to run code, okay. If you use such tools, this limit, you don't need to worry about exceeding this limit, okay. But if you are doing SSH telnet or SSH logging to the server and doing all the work on the server, and then there's this 2 session maximum limit. All right. Oh, after, so when Polly actually said that, hey, this is like 10 seconds remaining, counting down, you want to make sure that you close all the .go files you are editing, okay? And you definitely don't want to upload the .go files again after the exam ends, because we'll be looking at the timestamps of all the .go files you upload. If it exceeds the ending time, then again, the penalty here will be applied. All right, so make sure you do the last submit before the ending time. Make sure that you finish all the editing before the ending time, and quit your editor, okay, or quit your SFTP client. All right, and here's the process, okay. So be in the Google Meet session, and you know what is the link URL for the Google Meet session by 10:20 a.m. All right. Okay. If you can come 5 to 10 minutes prior to 10:20, that'll be even better. Okay. Polly can then start checking the student ID and match the photo to your face. All right. And as soon as you come, we do the check as soon as possible. So we might be able to start the exam at 10:20, the best. Okay. Now, in case we need more time, we might be starting at 10:25, 10:20 something, depending on when we're done checking the IDs. All right. So usually it will take some 10-15 minutes time to finish checking all you guys' ID. Okay. But if some of you guys come earlier, then it might be just 5 minutes, or maybe even less, 1 or 2 minutes after 10:20, we can then start the exam. That is also saying that we might be able to end the exam earlier than 12:10, the usual ending time of the lecture. And the total time you will spend on working on the exam is only 90 minutes. Sure, Ivan, feel free to go. Okay, and just make sure you come back to go through the list. Good. And the rest of the class, if you need to go, just go. Don't worry. Okay. Polly will say, let the exam begin when the exam time starts. Okay. And shortly, Polly would actually upload a PDF of all the exam questions on the score, exactly channel exam 1. Okay. So this way you can actually download the PDF file, okay, and skim through all the questions quickly this way. Yeah, so once I do that, once you go through the exam questions and go to the Google form link, fill the basic info, and submit the Google form immediately. All right. Bye, Yixin. And there are total 100 points to earn, but you only have 90 minutes to work on it. Okay, so you can actually get an estimate of time you spend on the questions. And bye, Amber. Yeah, feel free to go. Okay, so the PDF file might be a little bit pleasant to read if you need to scan through the exams. And Polly will actually also let you know if it's the halftime of the exam. At 85 minutes, Polly will also announce 5 minutes left. Okay, and 89, 1 minute left. Okay, at this point, definitely make sure you submit the Google form the last time. Okay, if no more updates necessary, and if you have more updates to do, make sure that you submit again within time. Close the file you are editing. When it's 10 seconds countdown, definitely make sure that you are done with everything. Okay, because there's also a little of delay in the Google Meet session. You might be able to end the exam. We might be able to a few minutes before 12:10. All right. If there's any question about the exam, ask vocally. Turn on your mic, ask vocally, or type up the question on the chat space of the Google Meet session. Okay. Polly would actually answer your questions either vocally or type and answer back on your chat entry. Yeah, and allow us 2 weeks to grade the exams. And that's the whole process. Okay, it's straightforward and yet a little bit uncertain for you guys being uncertain for you guys taking such an exam the first time. Okay, good. All right, that's all for today, and bye, guys. Okay, bye.